blank. So I showed this one at the beginning of last class. In 6.6, we learned about compositions of functions. It was one of the function operations we could do. And we learned about that so that we could learn about inverses. And what happens to take compositions of inverses. We learned about that so that we could understand radical functions as inverses of quadratic functions, which means that the shape of the graph of a radical function is the flip across the line y equals x of a parabola. Right? Here's the 1/2 of a parabola. If I flip that across the line, this is the line y equals x, I get the graph of a square root. Right? Well, the two functions that we got to learn about now are two functions that are also inverses. Today we do exponential functions, and then next class we learn about logarithms, which is a totally new kind of function for you. Probably, even exponentials are new, but probably logarithms are something that seem more bizarre than just an exponential function. So that's why these two sections get tacked on to the end of that chapter, which just talked about inverse functions, because these functions are inverses, and it's important. That's why we learn them together, because we need the two together in order to solve equations. So today is all about exponential functions. And you're going to see that most of these things, these were kind of the same objectives that we had for the graphs of radical functions. It just, now we're going to recognize the graph of exponential functions. We've had these same objectives many times, because the objectives actually don't say any one particular kind of function. They just say you're supposed to understand all the basic functions. So most of these are to know the basic shape, know how to move it around the graph, right? By adding, subtracting numbers, putting minus signs in front, that kind of thing. So an exponential function, Jose, right? Why don't you go sit in the back, right? Most of the time, when you don't know what a function looks like, really the only way you're going to have to tell is graph it. Plot some points and see what the shape looks like, right? Now, this is going to be the one example that I kind of use over and over to make the example. I could use a lot of different numbers here. It doesn't have to be 2 to the x, but I'm just starting with 2 to the x. Now, what makes that an exponential function? Where do you see the variable? In the exponent. That's why it's exponential, right? When a function has the variable in the exponent, that's the exponential function, right? So that's the first thing to understand. Variable in exponent. Right. It doesn't have to be just x. It could be 2 to the 2x minus 3. It could be a variable expression, but it's going to be a variable. It's in the exponent. And so we're going to plot some points just to see if we could tell what the shape of the graph looks like. And I've already started a table of values with 0, 1, 2, 3. Okay, thank you. I have no idea. Okay, today. So these are passes for SOLs for 3. So it's for now.
Teachers, excuse this interruption. At this time, please release all SOL catchers with an orange cap. Please release all SOL catchers with an orange cap.
Right. In the nick of time, they got those passes out here. Okay, so.
Mr. Botwinick, you're needed for testing at the Media Center. Mr. Botwinick to the Media Center.
Okay, you remember, where did I get the 0, 1, 2, 3 from? I made it up. I get to pick. You always get to pick the x values, right? So I'm picking them because I kind of know what the shape of the graph is, but the truth is you pick the x values. If you pick x values that don't really show you very much, then pick some more. But you pick them. Okay, so now one at a time, I have to substitute the x values here and figure out the y values so that I can plot the points. All right, well, what do I get if I plug in x equals 0? What is 2 to the 0? What is anything to the 0? 1. Properties of exponents. Anything to the 0 power equals 1. So this one is a 1. What is 2 to the 1? 2. What is 2 to the 2? 2 squared. 4. What is 2 to the 3rd? 8. So there's some points. Let's plot them. 0, 1, which happens to be the y-intercept. 1, 2, 2, 4, 3, 8. Okay, that's the starting point. Okay, now we need to see what happens when x is negative. Good. Okay, so I've already got these points on the graph. And you could do this in the calculator if you want. What do you get if you do 2 to the negative 1? Remember properties of exponents. How do you get rid of a negative exponent? Right, if I do 2 to the negative 1, you flip it to the other side of the fraction. So 2 to the negative 1 is 1 over 2 to the positive 1, which is 1 half, right? 1 half. But I don't want to make this an exercise in the properties of exponents. You know, if you want, just put it in the calculator, see what you get. What do you get if you put in 2 to the negative 2? Okay, 2 to the negative 2. What other people tried to. You should get 0.25, right? Which is 1/4. Oh, that's not good. Did it flip? No. Okay, what do you get if you do 2 to the negative 3? .125. It's actually 1 over 2 to the 3rd, 1 over 8, which is 0.125. Okay, now see what happens if I add those points to the graph, right? At x equals negative 1, I get half. X equals negative 2, I get 0.25. X equals negative 3, I got 0.125. Okay, now, what do you think would happen if I put in 2 to the negative 4? It would be even smaller, right? And if I kept going to the left, it's going to get smaller and smaller and smaller. Do you think there's any number you could put in for x? Any negative number large enough that would make y equal 0? And the answer is no. There's nothing. When the x as a negative number gets bigger and bigger and bigger, this thing's going to get smaller and smaller and smaller, but it can never equal 0, right? And when a graph has a line that it can never touch, it can never get to that x-axis where y equals 0, that's called an asymptote, right? And I'll define that on the next slide. But what we know is that this graph right here is going to go, let me change the thickness of the line. It's going to get infinitely close to the x-axis, but it can never touch it. Right? That's the shape of an exponential function, or at least one of the two kinds of exponential functions that we're going to see today. And you can notice First of all, most of the time when we do an asymptote, we do it with a dashed line on the graph. I'm going to do mine in red there, just because I can. A lot of times in the books, that's what they're going to use. And so this line right there, y equals 0 is asymptote. Do you notice, because it can never touch the x-axis, it doesn't have an x-intercept. It doesn't have a 0 or an x-intercept because it can't touch the x-axis. It does have a y-intercept. The y-intercept is 1. And you can see what the basic shape is, right? It starts out infinitely close to 0, and it slowly increases until it gets to the middle, and then it shoots up, right? It grows very quickly. Okay, let's see what happens if I do 1/2 to the x. So what have I changed? I've taken that number that's being raised to a power. Instead of being a number bigger than 1, now it's a number less than 1. Okay, and again, let's put it in the calculator and see what we get. What do you get if you put 0.5 to the 0? It's got to be 1. Anything to the 0 is 1. What if you get 0.5 to the 1? To the first power, 0.5. What about 0.5 squared? It's like 1/2 squared, 1/4. Right? And about 0.5 to the third. .125. If you notice, those were the numbers we got when we did the -1, -2, -3 for 2 to the x. So we've actually flipped sides here. Okay, now put in, what is 1/2 to the -1? 0.5 to the -1 is 2. How about 0.5 to the -2? 4. And 0.5 to the -3 is 8. So now, if I plot all these points, what I'm going to see is these are just the flip across the y-axis of the 2 to the x. This is hard to draw. I mean, it's still, there's, come on. That's not bad. Still, if you look at that, I can keep putting in numbers, right, bigger here, 3, 4, 5, 6. It's going to make that line get infinitely close to y equals 0, but it can never have y equals 0. There's nothing that you could put in here that would make that number equal 0. So it'll get infinitely close, but it's not going to touch. So it has an asymptote, just like the 2 to the x. There's the asymptote. All right, so those are the two basic shapes of exponential functions. Right? If the number which is being raised to a power is bigger than 1, then the shape looks like this. It's called exponential growth. Because as from left to right, it's increasing growth. Right? If the number which is being raised to a power 1/2 is less than 1, then it's called exponential decay, decreasing, right? Because what is it doing from left to right? Decreasing. In either case, there's an asymptote. Can't touch this. Again, so an asymptote, this is not the only time we're going to deal with asymptotes. We're going to deal with asymptotes for this, for logarithms, and then in the next chapter 9, it's almost completely about asymptotes. So this is just the first time we're going to see that. Now, if you've been in a chemistry class, something like that, if you've done half-lives, then that's exponential decay, right? Most of the wordish kind of problems that we do that involve exponential growth involve either like population growth, something you might see like in a biology class, or sometimes money, things like that. Sometimes like invest a certain amount of money, you get a certain interest rate, how does the money grow? Or even for this one here, depreciation. If anybody's family owns a business and you got to do taxes every year and you got to like declare like everything you own. Every year you're trying to take what you own and depreciate the value, right? That's exponential decay. So, I mean, they're very practical. They come into play a lot. So exponential growth, exponential decay. Right. Now, the basic form, they call it the general form, but, general, standard, whatever you want to call it, for an exponential function is actually a times b to the x. I mean, we've been dealing with only like the b to the x part. We had a number raised to a power. But you could multiply by a constant. It could have a number in front of it too. It would still be an exponential function. Now, for the purposes of what we're doing here, we always consider b as positive. We're not going to use any negatives. And b would never equal 1. b is either bigger than 1 or it's less than 1. It can't equal 1 because what would you get if you had 1 to the x? It'd always be 1. It would be a constant. All right? 1 to any power is just 1. So that's like in between growth and decay is just the line y equals 1. Good. Okay, so now what is the effect of that A? I did this already in the calculator just to show it. We don't have to plot points. I mean, for the most part, we're just looking for, sketching purposes, just to understand what the general effect is of doing these things. But just like we saw in the homework that we went over at the beginning, when you multiply a function by a constant, it either stretches the graph or compresses the graph. Right? In this case here, I'm graphing 2 to the x and 3 times 2 to the x. So the fat line is this 3 times 2 to the x. But what does it look like it did by multiplying it by a constant? It made the graph go up faster, right? So that is a vertical stretch. Now, if you look in particular, look at in the table of values here. When x equals 0 for 2 to the x, right? You plug in x equals 0, you're going to get 2 to the 0 is 1. Right? But now, for 3 times 2 to the x, 3 times 1 is 3. So actually that number, whatever is that number in front, that's the y-intercept. Right? That will be the y-intercept. Because when you substitute the x equals 0, the anything to the 0 power is 1, and that constant a, that's the y-intercept. So here it was at 1, here's at 3. And the whole graph is a stretch. So I'll call that a vertical stretch. And 3 there and there is the y-intercept. Now, when you're dealing with a function, which we will, when you don't actually use x as the independent variable, you use t for time because it's a real world kind of thing, then when t equals 0, that's like the initial point. It's the initial value. Right? If you're doing exponential decay, right, you started with a certain radioactive element, and the initial amount was what when you plugged in t equals 0 before you let time start going forward. Okay, so understanding that, here's the first thing. I mean, you're going to find this homework, these very easy, should be very easy. Here's a couple of exponential functions, right? A times b to the x, a times b to the x. The first question is, are they growth or decay? Right? Well, what are you looking at to tell whether this thing is growth or decay? Is the b greater than 1 or less than 1? And what is it? 0.95 is less than 1, which means it is decay. Right? If that number is less than 1, then it's going to decay. The shape of the graph would be like that. And what about this one? Growth or decay? Growth, because 2 is greater than 1. Right? And then the last, what is the y-intercept? Right? 12, it's the A. And what is the y-intercept? 0.25, right? So that is, come on. I don't want that there. Okay. This thing is being kind of funny. All right, so the first one, since b was in between 0 and 1, it's always positive. That's why the 0 is there. Then it is decay. You in here? You got a path to do an SOL. Okay. And then the intercept, notice the way they did the y-intercept, right? It's 12, but that's the point, 0, 12, right? X is 0, y is 12. And this one, because b is greater than 1, growth. And the intercept is 0.25. I mean, with that much information, you could pretty much sketch the graph. You know the basic shape, you know where it crosses the y-axis, you know that it has an asymptote on the x-axis, it'll never touch that. So you could sketch in a graph pretty quickly. So here's your first U try. Right. Do the same thing for those two. State whether it's growth or decay and what is the y-intercept. What'd you say in the first one? Growth or decay? The 4 is greater than 1, so it's growth. What was the y-intercept? Say again? 0, 3. Right? How about the second one? Growth or decay? Right? So 0.75, less than 1, decay. What is the y-intercept? 11. You know, we're not going to have a ton of like calculations and stuff that we do this with this, but you know, maybe if there's a little bit, still someplace we can make a little bit of a mistake here, which because we do a lot. Don't look at this 3 times 4 to the x and think that that's 12 to the x. It's not 12 to the x because the 3 is not being raised to the x power, right? It's only 4 to the x. Right? So don't ever try to multiply those two. Can't do that. Pretty easy so far, right? So again, this kind of relates this to real world kind of stuff. They're giving us an exponential function that now they're calling it A of t. Instead of y, it's A of t. It's a function. A is the amount. If you think of it in terms of like radioactive decay, it's the amount you had at the beginning. And because you're talking about time, you're using t as the variable. And you can see the a that we had, a times b to the x, we still got that constant a, the lowercase a. But you don't see the b, right? Instead, what you see is 1 plus r. And the 1 plus r could either be growth or decay. If the r is greater than 1, then when you go 1 plus r, you get a number bigger than 1, and it's growth. If the r is less than 1, then 1 plus a negative number, it's less than 1, it's decay. So they kind of slightly change the way that we define growth and decay for this real world kind of thing. If the r is greater than 0, it's growth. If the r is less than 0, it's decay. Okay, growth and decay. So it'll make more sense when we see it on something like this. Okay, modeling exponential growth. You invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? Is your money getting, you're going to have more money every year if you got 5% interest? I mean, you're adding to how much money you have, right? So definitely you know that this is going to be exponential growth. You need a number which is bigger than 1, right? I mean, this is a mistake even in the pre-cal. They do this all the time. They see the 0.0, they say 5%. Okay, 5% means 0.05 when you do it in a math problem, and they use that. But that's not correct. If I multiplied what I made this year by 0.05, I would get 5% of that. I don't want 5%. I want 5% more than I had the year before. So again, the way you get that is by doing 1 plus 0.05, 1.05. Now that is what you would call a growth factor, right? Because this is a number bigger than 1. If I multiply it times how much I started with, I'm going to get a bigger number. Okay, so this is what's being raised to the x power, or actually to the t power, right? And remember, the y-intercept is the initial amount. What is the initial amount? It's 1,000. We started with 1,000. So we can say that our amount, as a function of time, oh, I didn't write that, I need a 0, is 1,000 times 1.05 to the t, right? So for the first year, if I put in t equals 0, then anything to the 0 is 1, and the amount I have is 1,000. Right? After 1 year, then I would have 1,000 times 1.05 to the t. So what is 1.05 times 1,000? 1,050? 1,050? So it's growing by a little bit. Okay. So this is the initial amount. Right. This is 1 plus 0.05, right? So this is the R that they had on the last slide. Because the R was positive, that's a growth factor. It's growing. Now, if you were asked the question, which they have here, how much money are you going to have after 6 years? How do you think you'll calculate that given this function? T equals 6, right? If you want to know how much is in there after 6 years, then put in A of 6 equals 1,000 times 1.05 to the 6th. And that you can number crunch, which you really should try to number crunch this so that The first time you try this isn't in a test. To the sixth. Oh, that was wrong. Clear. 1,000 times 1.05 raised to the sixth. How much money do you have? $1,340. And usually, when you're dealing with money, you usually have two decimal places because make it sense. In this case, it looks like it'll be 0.10. So 13.40 and 10 cents. So try to do the same thing with this one. Now the initial amount is 500. The interest rate is 3.5%. How much will you have after 5 years? Who's got a number? How rich are you? Anybody get an answer? How much you got after 5 years? Karen? 15? No? Right. So again, in this formula for growth through decay, that lowercase a, that's the initial amount. What do I put in for that? 500 is the initial amount, right? 500. Right. What is going to be raised to the t power? Well, if the percent increases 3.5%, then it's going to be 1 plus 0.035, right? That's what the R is. So 1.035 increase. So that's the function. Now you can use that to do any number of years, but they ask specifically for how much after 5 years. So what are they asking you to do with that? How do I find how much is there after 5 years? Sean? T is 5. A of 5 equals 500 times 1.035 to the 5. 593.84. And that's kind of how it works, right? When you put money in a bank account or something, an investment, it's kind of how it works. Not exactly how it works. In fact, you don't get it. This would be called, if we just use like 3.5% per year, that's a simple interest rate. But most of you, if you put any money in anything, you get a compound interest, which is a little bit more than just straight whatever that interest is. But we're not going to do compound interest in here. Okay, so growth and decay. Now this switches to the next section. That's all we're going to get out of the first section. The second section is more about the graphs and how do you transform them by adding, subtracting, multiplying, putting minus signs in there. Right? We already saw what happens when you multiply by a constant. Right? The 3 times 2 to the x was a vertical stretch. Okay, what happens when you multiply it by a number which is less than 1? Right? In this one, this is the 2 to the x. The fat line is the 1/3 times 2 to the x. What did it do to the graph? It makes it go up slower, which is called vertical compression. Vertical compression. But, I mean, we know more than that. What does the 1/3 represent? It's the y-intercept, right? And you can see here when x equals 0, which is on the y-axis, y is 0.33333, which is 1/3. So it's still the y-intercept. So multiplying by a constant either stretches the graph or compresses the graph. Okay, now what happens when we put a negative in front of a function? Generally speaking, it flips it, right? So here's the y equals 2 to the x. Here's the y equals negative 2 to the x. It just takes all the y values and makes them negative. Right? Does that change the asymptote? No. Still, this graph is going to get infinitely close to the x-axis from the bottom, but it's still not going to touch that axis. So this would be a flip cross x-axis. You can see, look at all the y values. You know, here's 1, 2, 4, 8, -1, -2, -4, -8. We're just putting a negative sign in front of all of them. Okay, so for most of what we're doing here, you're not going to be asked to sketch a lot of graphs, but you should be able to describe what's going on. I mean, even in their problem here, they just say, how does the graph compare to the parent function? They didn't actually ask us to graph it, although you're going to see that they did graph it, but they didn't actually ask you to do that. I mean, first of all, this y equals -1/3 times 3 to the x. What do you think they mean by the parent function? I mean, you got to compare it to the parent function. What do they mean by that? The thing with exponentials is that it could be different. Like before we were using y equals 2 to the x, so that was the parent function. But now the parent function is y equals 3 to the x. It's still exponential growth. It's going to go up faster because it's a 3 and not a 2, but it's still exponential growth. That's what we mean by the parent function. All we really want to know now then is, what about this -1/3? What 2 things is that doing to the function, to the parent function? The negative is a flip, and the 1/3 is a compression. That's it. You just have to say those things. Flip, compression. So we're going to say flip, so they do have the graph here. You can see definitely it's been flipped. And you can see where this one had an x-intercept, a y-intercept of 1. This one is not -1. It's -1/3, going up a little, going down a little slower. So do the same thing for this. Describe, just describe what is going on. I mean, what is the parent function and what is going on by what they're doing to it. What is that? What did you say is the parent function? 5 to the x. Right? Okay, and what two things are going on because of multiplying by a -0.5? Flip, compression. Good. Okay, now we get to the other transformations that we've dealt with. Actually, we just did it in the homework for the square root function, right, where we're going up, down, left, and right. This is going to be the same kind of thing. Remember, in the square root function, if the parent function was the square root of x, then y equals the square root of x minus 4. What is the -4 doing? So right 4. That's the example. That's what it looks like for an exponential. The 2 to the x minus 4 means that's a shift of right 4. It's exponential growth. The parent function would be 2 to the x, and it's right 4. And that's all they asked here is just describe it. Right 4. What would be the y-intercept? Remember, it's a times b to the x, and that a is the y-intercept. Do you see anything that's multiplying here? And the answer is no. So what is there? 1. The y-intercept would have been 1. If I was going to sketch this graph, I would say, okay, well, I know that the parent function would have had a y-intercept at 0, 1. So I'll move it 4 to the right. And then because it's growth, I know that it would have this kind of a shape. So a minus inside means right 4. And I mean, it is kind of important. Does moving the parent function graph to the right 4, understanding that we had an asymptote right on the x-axis, if you move it to the right 4, does it change the line? If you move a horizontal line to the right 4, isn't it still the same line? Yeah, it doesn't change anything at all. Okay, let's see. Now we got a few more things going on. First, what kind of function is this, growth or decay? Decay because that's a 1/2, right? So this is decay. And what would that make the parent function? Yeah, 1/2 to the x. So now our question is, how is this 20 and 10 changing the graph? What is multiplying it by 20 do to it? Deshaun? Stretch. Right. This vertical stretch. Okay, now what does it do to the graph when you add a number after the function? Up, down, left, or right? Up, right? So that would take the whole graph and move it up 10. So if I was going to sketch this graph, I mean, first of all, if I didn't have the up 10, I would say that thing had a y-intercept of 20, right? Whatever that number is that's multiplying 1/2 to the x, that's the y-intercept. So there would have been the y-intercept. Now the y-intercept is going to be 30 because you're adding 10. So this thing, if I was going to draw it, I mean, I would have to make sure my scale made it look like it. There's 30. Now, if I take a graph and I move it, if I take the parent function graph and I move it up 10, does that move the asymptote? The asymptote was here. If I move the whole graph up 10, does that move it? Yeah, so the new asymptote would actually be at 10. And usually then we would sketch that in. And then the shape of the graph, because it's decay, should be like this. Not too hard? Hope. Okay. Okay, so just describe the transformations of these two. What did you say in the first one? +2 inside the function means left 2, right? It looks like there's two different things going on in the next one. What does this 5 do to it? Stretch. Vertical stretch. And then what about the +5? Up 5. So we just, again, this, how you graph by using transformations, it's something that's been with almost every function that we've dealt with. We've had to do this. And it works the same way. right? Kind of like conjugating a verb in another language. Good? Okay. Now, we are also asked to, be able to do scatter plots. I mean, in the end, we've done scatter plots so far with linear, quadratic, cubic, quartic. All those were in our menu options, right? And you could be given data and not told what kind of function it is. You just look for the shape of the data and see what it is. In this particular problem, says the best temperature to brew coffee is between 195 and 205. Coffee is cool enough to drink at 185. The table shows the temperature readings from a sample cup of coffee. How long does it take for the cup of coffee to be cool enough to drink? Use an exponential model. Well, what did we do before when we were presented with data and we wanted to make a model out of it? You got to go stat edit, right? And you can do it if you want. I've already put it in here. Stat edit, right? And I've got all these values are underneath the X or L1, and these are the Y values underneath the L2, right? How do you look at the data? If we didn't know we were using an exponential model, how would I look at the data to see the shape? Second, Y equals stat plot. Remember, you got to turn it on. Otherwise, it's not going to show you the plot. So let's turn that on. One, on. And then remember what the next step was? So that it zooms in on your data. Like right now, if I hit graph, it's showing me those. I can get rid of those. Clear. Clear. Remember, zoom 9. And so there it's plotting the points there. And, if you were given that data and not told what kind of function, hopefully you would look at it and say, looks like exponential decay. Looks like exponential. Then how do you make the model? Well, you make the model, if you've decided you want to make an exponential model, the same way we did before, stat, calc, and then you got to look for exponential. We used only these 4 right here, but if you keep going down, you're going to see there is an exponential. The 0, exponential. Exponential regression. It's like a best fit model to go through those points. And we hit enter. Enter. So it's giving us that A times B to the X. The A is 196.657. The B is 0.977. The B is less than 1. Decay. Okay. So we could do the same thing. Again, you don't have a calculator to take home and do this, so I'm not assigning any problems like that, but I just wanted to show you we could use the same procedures we did before for exponential data. All right, we just got to go to a different place in the menu at the end. Fatto, done. So we basically did all the kind of things that we've done. First, we introduced ourselves to what's an exponential function. What does the graph look like? What are the particulars, especially the asymptote is a new thing. And then we moved it around. We learned how you can use it in a practical way, right? Exponential growth, exponential decay, and then we moved it around. So in the homework, right, from the first section, this 18 to 24, it's like where we did, you just have to say, is it growth or decay based on the value of B and what is the y-intercept? Those should go pretty quick. Right, the 27 and 28, they're giving you an initial value and a growth rate or decay rate. Try to do like the one example we did. And then these 4, 7, 9, 17, and 19, it says graph, but you really just describe the graph. Describe what were all the transformations. That's enough.